seems to be working just fine. Good. Seems to be working just fine. Oh, there may be a bit of a delay. That's interesting.
Okay, so feel free to share your screen. You can test, and then you can just take control.
Let's test it. Let's test it. Let's see. Share. This will stop the screen sharing. Do you want to continue? Oh, it's going to stop your screen sharing if I do that. Okay.
Yeah, please do. Please do.
Where do you want to share? I want to share. I guess it's the desktop. And now what I'm going to do is switch to slides. Now, do you see a slide?
Not yet. So let me see.
Oh, I need to click on this thing here. What's it doing? Zoom wants to share the content screen. Choose what you'd like to share. Okay. That doesn't seem right. You're sharing my screen. Do you see what looks like a slide?
Oh, yes, no.
Very good. Okay, so I'll stop the sharing for now until you do the introduction, okay? If I can find.
Yeah, actually, it's okay. You can just share. No, it's totally okay. You can, unless you want to modify your slides. Otherwise, I think you can just share now.
No, I don't want to modify anything. This is fine.
Okay. All right. So then let's.
So
just have this
edit. Until we start, I think I'm gonna. What am I gonna do? I'm gonna see if I can see you guys, which I can't. All right. I guess that doesn't matter. Oops. There we go. It seems okay. Yeah, it seems to work. Very interesting. Zoom for Harvard. Did I lose you? I may have lost you. Join a meeting in progress. It says I'm still there. Okay, good. Oh, there's Rajmani. Hi, Rajmani. Hmm. Am I still connected to you guys? I'm not sure this is working. It says I'm sharing. There are 13 participants. Is anybody there?
You were there, right?
I was there. I'm going to stop the share and restart it, I think.
I think that's the best way to do it. That was going to be my suggestion.
Let's stop this. All right, now I'm back again. Seem to have lost my share. Hello, I see you back now.
No, but are you ready for the sharing?
I'm I stopped because everybody seemed to be gone, but I'll try.
No, everyone is here. Just wait.
Okay, so let me try the sharing again. Now what's it doing?
Once you share the slides, I think you may not be able to see other people, but we are here.
Okay, so just a minute. Share my entire screen. Share. Oh, that looks good. Is it working?
Yes. Yeah, just don't move, and I think we can. Yeah.
Sit here.
Okay, so maybe shall we start?
Sure. I don't
Okay.
see my. I
So,
need to turn
yeah.
on my camera here. Must be a way to do that.
I think when you share the full screen, if you're using a laptop, you may not be able to see other people, but that's okay. I think
Okay.
I'll help you. Yeah. I'll help you.
Let's see. I don't know how to turn the camera on.
Your camera, yeah, it's not on.
Okay, so I guess it doesn't matter, huh? At least I can hear you, so that's good.
Okay. Welcome, everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. Today, we are very honored to have Professor Michael Creutz from Brookhaven. And Professor Michael Creutz is an expert in chiral fermions. Originally, there are a few series of talks earlier related to chiral fermions. I thought Professor Creutz might be good to comment about this. Professor Creutz decided to talk about another possibly interesting work from his own choice. He will be speaking about QCD beyond diagrams. So let's welcome Professor Creutz. And every audience should feel free to interrupt and ask questions anytime. So yeah, welcome. Please take over. Thank you.
Okay, so thank you very much. Although I guess I'm not going to explicitly talk about chiral fermions, it's kind of closely related. Okay. Excuse me. So this is based on a talk I gave in Singapore a couple of years ago at Feynman's 100th birthday celebration. I took most of the directly Feynman related stuff out. I recently wrote it up. It's an archive, well, this number here. And the talk itself I gave in Singapore is available online. Whoops, now what happened? I lost my thing. So if people want to see it, you can. Okay, QCD has some interesting properties which you really don't know how to see in Feynman diagrams. Of course, the most famous is confinement, the fact that free quarks don't exist. It has the interesting property that it automatically generates mass. You have to have a parameter in lambda QCD of dimensions mass, and everything with mass is proportional to that, at least without until the quarks get mass. And it has the property of chiral symmetry breaking. The Pion and the rho are both made of exactly the same quarks. The only difference is their spin structure. but the Pion is much, much lighter, and that's understood through chiral symmetry. And then there's an interesting, QCD is another parameter which you can't see in perturbation theory. The different values of this parameter theta have identical perturbative expansions, but they're different in physics, and I will discuss that. Let me take a little sip of coffee here, the water. Okay. Now, basically, our understanding of most of quantum field theory is through path integrals. So I'm just going to do remind you of some really old things. Feynman in 1948 discussed summing over all the paths a particle could take. So this would be space, this would be time. And he showed that if I integrate over all possible paths, in a sense to be defined in a moment, either minus the classical action, that's proportional to the trace of a quantum mechanical operator, either minus beta h, where this S is the classical thing, and the Hamiltonian involves non-commuting operators, X is I. So what this means is d-dimensional quantum mechanics is equivalent to d+1 dimensional statistical mechanics. Why does this keep switching slide? So this this path is kind of like a classical worm, which is wiggling like mad. And this classical wiggling worm is equivalent to the quantum mechanics of the particle and the potential in one dimension. So this is basically the heart of the lattice gauge approach to Monte Carlo. In field theory, the paths become what are usually called configurations, but configurations are what are the paths of the path integral. Now the path integral, to define it, divide its time into little discrete steps, and then you have to take the limit when the step size goes to 0. An interesting feature of these paths is that this worm is extremely wiggly. A typical path is not differentiable. So the average of x dot squared, which you can define by taking it one time minus the previous time over a squared, diverges. So this has important aspects in field theory too. The typical configurations are not differentiable. Okay, well, the usual approach to field theory, you take your action and take off a piece S0, which is free particle propagation, and then you let them interact. And this gives you the Feynman diagrams, which are drawn all over Feynman's van here. But the path integral is much more general. It doesn't require perturbation theory. Now, the electroweak theory, this coupling constant alpha is very, very small, much less than 1. And for electricity and magnetism, perturbation theory works perfectly for all practical purposes. But Dyson showed that perturbation theory cannot converge. And he had a very simple argument for this, which is kind of fun to repeat. If it was a convergent series, you could imagine taking E to IE. That would make like charges attract. And this would, in fact, be an unstable vacuum, because if I make a big blob of minus charge somewhere and a big blob of positive charge somewhere else, I can set up a free generator of power. I just take and produce an electron-positron pair somewhere, make the binding energy to this larger than the rest mass of the electron, and put the positive in the other bucket. You just can start making more and more energy, and everything would blow up. So perturbation theory is known not to converge. Now in QCD, if I turn off the coupling constant, I have free quarks and gluons. I turn on the coupling constant, I have physical particles, protons and pions. The spectrum is qualitatively different. So you can't really expand this spectrum to get that spectrum. So you must go beyond perturbation theory to get the usual flux tube connecting quarks and antiquarks and the confinement and all that. Now we all know field theory has got divergences in it. You have to cut it off in some way, and then you remove the cutoff by a limiting procedure. This is standard renormalization. And the idea is that you adjust your coupling constant, holding physical quantities fixed. Now, most regulators are based on perturbation theory, polyvolars, dimensional, etc., where you start to calculate, you find a divergent diagram, and then you cut it off. But QCD doesn't. You have to go beyond perturbation theory, so it requires a non-perturbative regulator. And that's exactly what lattice gauge theory is. The lattice spacing itself is a cutoff. So you take space and time, divide it up into a bunch of discrete points. Any path that a quark might take through this lattice is replaced with a bunch of discrete steps. Now, as sort of a thought approach, you can imagine using the proton mass as your physical observable. This is not, of course, what is done in practice, but it's a nice way to think of it. The proton mass on the lattice is going to depend on your coupling constant and on the lattice spacing. And your coupling constant is supposed to depend on the lattice spacing in a way to hold the proton mass fixed. So the derivative of the proton mass with respect to A is supposed to vanish. And it's by chain rule, this is two terms. Differentiate with respect to the coupling constant, and then how the coupling constant varies, and then just differentiate directly on the second variable. Now, in the theory, the lattice spacing is the only dimensional thing, at least until we put the quarks in, which we'll talk about later. That the second term is known. It's just minus and proton. So if you want to know how you vary the coupling constant with respect to the lattice spacing, And this thing is called beta of G. It's just the definition. It's just the mass of the proton divided by the derivative of the mass of the proton with respect to G. And this tells us exactly how to take the continuum limit.
Excuse me, I have a question.
Mm-hmm.
So wonder, so when you choose the latest, when people choose the latest cutoff, and maybe also the latest regularization, like, I mean, possibly people usually just do a square cubic lattice type of regularization, but in maybe more condensed matter way of thinking, you might have a different way of regularize the system. I just wonder whether this input has any maybe effects on the output mass spectrum, perhaps by some scale, a little bit scale difference. For example, maybe the Google or Pion or the proton mass might slightly different if we choose different regularization scheme. Regularization in the sense of how you put on latest.
I think
yeah, this is just
the assumption is as lattice spacing goes to 0, it's really independent of the details. Of course, we don't have a proof of that. You don't have to use the proton. You can use some other particle to fix it. In fact, generally, some people have used the omega minus as a thing to hold the thing fixed. So there's kind of an assumption here, and whether it's a hexagonal lattice or a cubic lattice, whatever, we usually assume that doesn't matter. I guess until you get down to the details of the fermion, the Dirac operator you use, then there can be subtleties of doubling, etc., which can depend on your details, which is not something I intended to go into in any detail here, but there is a bit of an assumption here. But the idea is that all other, well, it's sort of a matter of universality that we believe in the continuum limit. It shouldn't matter the details.
Okay. All right. I suppose, viewing the QCD as some intermediate energy scale for field theory, not as the UV cutoff for the latest regularization. And I think your point is that it should be independent. That's probably what you say, right? It's independent.
It's a question of universality. As long as you're going to the same fixed point, it shouldn't matter. But there might be another fixed point. So it's a bit of an assumption here. Yeah.
Okay. All right. Thank you.
Okay. Now this beta of G is, of course, is well known to have a perturbative expansion. Even though we want to do non-perturbative physics, this does have a perturbative expansion. Starts off as G cubed and then G to the fifth. And these coefficients are known, and this is how Gross, Wilczek, and Pulitzer got a Nobel Prize, by calculating this. And the second term was calculated by Caswell and Jones. This NF is the number of flavors in the theory. Now, the important thing is that these two coefficients are universal. They're totally independent of the cutoff scheme, and therefore it applies to the lattice as well. And then you can take this differential equation, AD by dA is this beta of G, and take this perturbative expansion and actually solve it. Tell you how A depends on the coupling constant. And when you solve it, you get an integration constant, which is called lambda. There's a certain power of G. And then there's this interesting factor of e to the 1 over G squared. So this is non-perturbative. You can't expand an exponential 1 over G squared in the powers of G squared. So even though we started with a perturbation theory for the beta, you get this non-perturbative behavior, which is really a remarkable thing. But we do have to introduce an integration constant. Okay. Oops, I went the wrong way. Okay, now this integration constant is where the scale comes into the theory, that the mass of the proton must be proportional to this integration constant, which means that the proton mass has a non-perturbative expansion here. be the minus 1 over g squared. And this phenomenon of turning coupling constant into a scale has been giving this wonderful name, dimensional transmutation, by Coleman and Weinberg a number of years ago. So the renormalization means that the theory doesn't really depend on a coupling constant. It depends only on an overall scale. It's kind of a nice result. Okay. Now, of course, the masses of the quarks also require renormalization. I'm not going to go into that in great deal of detail, but it means you have to hold more things fixed. The mass is, the bare mass is supposed to scale as some constant times g to the power. This constant is another integration constant. And gamma 0 is also known. So you get one integration constant for every parameter in the theory, one for each of the quark masses, and you have the integration constant lambda. And because g is going to 0 in the continuum limit, so is the mass going to 0 in the continuum limit. So the way you take the continuum limit in the theory is you take both the mass and the coupling constant to 0 in a well-known way, precisely known way. And you get a bunch of integration constants, the masses and the lambda parameter. Now the details of what these numerical values are does depend on your lattice scheme and details. So that can vary. These things can get mixed up in each other, and I will say a little bit more about that later. Now, okay, so we've argued that the theory is non-perturbative. That actually also happens in the classical theory. And the importance of this will become clear in a minute. It's tied to topology. It turns out that having f go to 0 at infinity does not mean that, well, anyway, if you integrate FF dual over all space, it has to be an integer. Oops. Hitting too many things here. And this has to be an integer. And the importance of this is tied to the Dirac equation. When there's non-zero winding of the gauge field, the Dirac equation will have 0 modes, where this is the usual Dirac equation, will vanish on these functions. And these 0 modes are chiral, that they gamma 5 on them is either positive or negative. And there's this famous index theorem that the winding number is the difference between the number of positive eigenvalues and negative eigenvalues of gamma 5. All the other eigenvalues of the Dirac operator occur in chiral pairs, so there'll be a positive one and a negative one. Now, the importance of this was emphasized by Fujikawa, because we know that configurations with non-trivial winding number exist. And we look at on these, we can define gamma 5 as the sum over all the modes of the Dirac operator, the expectation rate of gamma 5. And that must be the winding number, because the 0 modes are there and they have a definite winding number. All the other modes than the 0 modes are above the cutoff or pair, depending on the details of your cutoff. And the importance of this is that if I take my Dirac op field and try and do a change of variables by multiplying it by an e to the I gamma 5 theta, this is not a symmetry, because the gamma 5 is not traceless, and it changes the fermionic measure, d psi, which becomes the new d psi times the determinant of this thing, and the determinant of this thing is e to the trace of the log of the thing, and so it's just it introduces a phase into the path integral. So if I try to do this change of variables, I get a new theory. And this is supposed to be the explanation why the eta prime particle, which is not a Goldstone boson. But the important point is that QCD has a hidden non-perturbative parameter theta. And for each value of theta, the perturbative expansion is identical, because in perturbation theory, the trace of gamma 5 just vanishes. just to comment on the three flavor theory, a couple comments on it actually. We know what beta is in three flavor theory, which means the lattice spacing goes as a certain power of 1 over the coupling constant. If I stick the instanton action in here, it goes as a different power of coupling constant. So even in instanton action is a very high power of the lattice spacing, whereas mass of the eta prime is going as eta to 0 because it's a physical object. So a message in here is that the classical instantons are not enough. You really need winding number, not over the classical thing, but over the fluctuating non-differentiable vacuum. So you get a much bigger power. And just, I left in one quote from Feynman: nature isn't classical, damn it. If you want to make a simulation of nature, you better make it quantum mechanical. And it's a wonderful problem because it's not so easy. I've had people tell me you can forget about instantons on the lattice because of this negative to the 9th power, and that's just wrong. Okay, for three flavors, if I take theta of pi, I'm basically flipping the sign of the mass, taking m to minus m. So three flavor QCD with negative masses is a different theory than three flavor QCD with positive masses. In perturbation theory, the sign of the fermion mass is totally a convention. So you see the perturbation theory doesn't, well, it's a different theory. And yet it has the same perturbative expansion. Now, theta is known to violate CP. Experimentally, CP in the strong interactions is very, very small. And this is a puzzle which I don't really have a solution to, so I will just mention that. I'm going much too fast. Oh dear. Okay. So now let's comment a little bit on the masses. Quarks are confined. They are only in, in triplets and protons, etc. So how do you define their mass? Physical particles propagate over long distances. You know what the mass of a proton is. It's just the usual expansion, mc squared plus a half mv squared, etc. But quarks don't propagate alone, so you can't do this. So how do you define the mass? Well, natural thing is I have this integration constant. I can just define quark mass to be this integration constant. The problem is that this is not unique. It depends on the detail of the regulator. It's well known that lambda with different regulators can be different, and that is the case for the masses as well. And it's even worse than that. We've got the integration constant m and the integration constant lambda, and they're both dimensional, and they can get mixed up with each other as well. And the details of that mixing depends on the lattice scheme. Now, to see that there's really a problem, it's convenient to look at the neutral pion. This is a bound state of both left and right-handed quarks, and it involves both the up and the down quark species. So you can do a thought experiment. You can create a pion with a UU bar somewhere, and then later on destroy it with a DD bar, because it's a coherent mixture of the two things. And as it propagates, lots of things can propagate. The pi naught is there. There's also heavier stuff, the eta and the eta prime. But this process of converting a UU bar into a DD bar is a spin flip process. The U is flipping from left-handed to right-handed. This says that spin flip processes are not suppressed at small masses. These things can't cancel because they're all non-degenerate. The eta gets a mass from the strange part of quark, and the eta prime gets its mass from lambda, as I said earlier. This fact that there can be a spin flip process involving multiple quark species is what is sometimes called the Tuf Vertex. I pointed this out a long time ago. Now, in perturbation theory, the left-handed and right-handed fields decouple when the mass vanishes. but that's simply not true non-perturbatively. And it causes this interesting mixing of the different quark masses. I'm going to take that previous diagram and close this with, say I give the down quark a mass and not the up quark a mass. Well, I'm going to generate a quark mass for the up quark because the down quark, if it doesn't vanish, I've got this process right, which is just basically the closure of this last thing. And this is non-perturbative. It's coming from the topology. And this process entangles all the masses and lambda. And because remember, lambda is in the eta prime, so that's in this picture. There's also perturbative corrections to this. So this has turned out to be a rather controversial thing. But you can't really separate the perturbative from the non-perturbative thing here. It's a property of the bound pions. Now, chiral symmetry gives us an extra handle on this. And if the quarks are light, we have predictions like the pion mass squared is proportional to the mass of the quarks times the lambda parameter. That's good old PCAC. So massless quarks imply massless pions. So for degenerate quarks, the idea of a massless quark is a well-defined thing. But if the quarks are non-degenerate, it gets more complicated. The chiral perturbation theory tells you the mass of the pion is proportional to the average of the up and the down quark mass. Now you can take this kind of formula and do it for various pseudo-scalars and put them all together. You can make an estimate for the ratio of the up to the down quark mass, which is, this is one particular combination. It's about a half. So the up quark is about half the down quark mass. But this has lots of caveats. First of all, this is only the lowest order prediction, and higher order corrections are not included, and they can have some ambiguities in them. There's QED issues of QED things. I've taken this combination, which tends to cancel out the QED corrections as due to a theorem due to Dyson years ago. And isosyn breaking is observationally very, very small. And the ratio of the pi naught, the pi is going to be lighter than the pi plus because of isosyn breaking, because the two quarks are not degenerate. But it's something that comes in at a higher order. The difference of the up and down quark mass is squared over, say, the lambda squared. But this correction is not controlled by chiral symmetry. In fact, it involves some kind of new, what are sometimes called low energy constants. And now, since this is quadratic and this is linear, it turns out that a fixed quark mass ratio as I'm renormalizing is not the same thing as holding fixed particle mass ratios. Despite people often claiming that the ratios of quark masses are renormalization group invariant, that's actually not true. It depends on the details of your renormalization procedure. If I fix particle masses ratios, the quark mass ratios will not. The trouble with this Zoom business is I don't get to see how people are reacting to anything, which is an issue. Okay, it's interesting thought experiment to imagine making isosyn breaking larger than it is. I mean, we know experimentally it's kind of small, so it's a good symmetry, but this formula that is proportional to the average quark masses has some amusing consequences. The mass cap is still there if I make the up quark mass vanish. If the up down quark mass just doesn't. And everything behaves smoothly as we go through mu equals 0. You get sensible physics if mu is a little bit negative. This is, again, not perturbative. The sign of the mass is a convention. In ordinary perturbation theory, you can use a gamma 5 rotation to flip 1 over p slash plus m to 1 over p slash minus m. That's not true non-perturbatively. Now, what happens if I keep going? Something interesting will happen if the up quark mass is down near the negative down. If the up quark mass is near the minus the down quark mass. And so what can happen, here's, okay, so this will be the mass of the up quark. Here's the down quark mass, which I'm going to hold fixed. As I come away from the isospin point, the neutral pion gets light, a little bit lighter than the charged pion, but eventually it's going to get down near 0. And it will happen before minus MD. The neutral pion will get massless. And when I go past that point, the neutral pion will condense. You get some kind of expectation value for it, which is a very strange thing because this is a CP object. This funny phase, once the neutral pion gets a mass, you get a neutral pion gets negative mass, will violate CP because this will get an expectation value. And Dashan kind of mentioned this in this really old paper before QCD was even known. It's not exactly at minus MD because of, because the pi naught becomes lighter than the pi naught, the pi charged pi. All right, so you can do chiral perturbation theory and kind of explore what happens as a function of the up quark mass and the down quark mass. And if I hold MD fixed at some value here and come down, I eventually hit this weird phase where this pi naught is condenses, the CP violating phase. Yeah, I'm definitely going to finish much too early because I'm going too fast. Well, it's interesting to look at the symmetries of this diagram. First of all, if I interchange M up and M down, it's symmetric that way. That's isospin. So if the two are equal, that's a renormalization group invariant. If isospin is exact. There's a symmetry under flipping the sign of both the up and the down quark mass. That's symmetry this way. In the usual chiral symmetry language, the condensate is positive here and the condensate is negative here, but it's the same physics. And that flipping about the signs of both is a symmetry in the sense if I take e to the I pi tau 3 gamma 5 times psi, I will flip the sign of the masses. And this is a valid symmetry because even though the trace of gamma 5 doesn't vanish, the trace of tau 3 does. However, this diagram has no symmetry under flipping the sign of only one quark mass. If we flip the sign of the up quark mass over here, you're in the other region. This means that the non-degenerate massless quark is not protected from renormalization. Mu equals 0 is not a renormalization group invariant concept. Physics goes smoothly as you go through here. I kind of need people to ask questions or something. Anyway, should we care if the quark masses are fuzzy? Not really well defined. You don't directly measure the quark masses in scattering. And this fact that...
Sorry, let me ask something. Sorry, the previous slide. Is this figure, the previous slide, is this figure, how is this computed? Just
okay.
Numerics and which numerics was.
Okay, so this diagram comes from and I guess I didn't write the formula down. In chiral perturbation theory, this occurs only as soon if you take the 3 quark theory, with the strange quark being heavier, you can calculate the masses, and there's a mixing between the eta and the pion, which is what gives let's go back one more. Back. Yeah. Naively, we would think something weird would happen at mu equals minus md, but if you take all three of them, I wish I had put that formula in here actually. When you have mu, md, and an ms, and you write down the most naive formula for the mixing of the eta and the pi. Let's see, what do I want to do? You find that the Pion mass does vanish at some particular value, which is involves the square root of all the. Where can I find it? I don't think I have it in these slides. But it's you just take the simple chiral perturbation theory where you write an effective field as e to the sum of the Pion fields times their masses. And oh dear, I shouldn't. Anyway, it's fairly straightforward chiral perturbation theory to get this diagram. It turns out that when the strange quark is finite, there's actually another region hidden up here where when both m down and m up are much heavier than the strange quark, that kind of flips around. So there's other regions, but this is because the strange quark. Well, I'm wandering.
So Mike, this is David Nelson. I have a question about this phase diagram as well. How does the CP phase pinch down as you approach the origin? Is that understood?
Well, this is the usual chiral picture where psi bar psi has an expectation which is positive here and it's negative here. What happens if I follow a line parallel to that, psi bar psi gradually decreases because you're decreasing the masses, but then it smoothly goes from a positive value to a negative value as you go around it. And in a sense, the expectation value of the sigma field you gain that pi naught expectation value, and you go around the chiral circle from one side to the other side smoothly. There's 2 second order transitions instead of the usual picture of the.
But there's some like a critical exponent or something that tells functional form of the.
Here will be Ising-like because it's basically one order parameter, which is the expectation of the Pion field. And this, I guess, is supposed to be an 04-like, if I remember what the lore is.
As we would have called that a bicritical point, perhaps.
I guess that, yeah, I'm not familiar with the solid state language on this, but so you have here you would have 2 second order transitions as this order parameter sweeps around from one side to the other, and then it's pi naught no longer has an expectation value in either of these regions.
Thank you.
It's actually a fascinating phase diagram because if we really keep the strange quark mass finite, there's another region hidden up in here, which I wanted to keep simple.
Actually, if you don't mind, since you say you go too quick, I think there's a lot of things to discuss for this diagram. If you don't mind,
I do not mind actually. I that's the trouble with these Zoom calls. You don't get as much interaction as you would like.
Okay, so this diagram we take a color NC equal to 3, and we don't have a 2 flavor, correct? And U and D.
The basic idea of this figure is that 2 light flavors, and there's all other kinds of other physics up above. So you can get it with just a 3rd quark. I think it's.
That's fine. We can fix the model and then we discuss the consequence. So the model is just 2 flavor.
Well, 2 flavor, but I did bring. It's actually really 3 because there's got to be a heavier thing there, which could be the eta or the eta prime. But you need to have. Let's back up.
We can fix one model, and I will ask more questions after we fix the model.
But yeah, this formula here, there's also an MS term, d minus mu over ms squared. So this is from the mixing with the eta, and there's another term from the mixing with the eta prime.
But this diagram, we really just have a U and D, right?
U and D and the curvature away from just, if it was only this formula, that would just degenerate down to a single line. But when you bring in the mixing with the strange quark, it opens up that funny region. The pure two flavors is kind of singular. And so it's nice to have the third flavor to have this open up.
Okay,
I
then
want to find that formula somewhere. It's certainly in the paper, but anyway.
okay, then let's consider maybe the spectrum. I suppose we consider the energy spectrum. So what do we see? Are there always some massive pions in this phase diagram, or somewhere maybe you say when mu and md is 0, you don't really have a massive pion? That part, I think I needed some.
At this point, there's actually, as you go across this, it's a first order transition. I'm sorry, I was being too quick. It's a jump. This order parameter psi goes from being positive to being negative. So at this point, they actually come together to be first order. Right at this point, there's 2 second order transitions come together. So this is actually a jump. But I think it's a little more subtle than that, because the yeah, it's really a segment kind of model, and there's a massless particle, so it's not. I think it's supposed to be O4 like, but sigma jumps, but the pions do become massless here. So there is some massless things here. Anyway, should I proceed, or I'm almost done? So
Okay, but let me just make sure this diagram is basically widely accepted. Is a diagram from certain paper, or is just widely accept the results? I was not I'm not sure what's just who produced this diagram basically, you know? And what's the ambiguity of this diagram, or is everything clear about this diagram? Basically,
well, it's funny, when I published this diagram, somebody said he thought he had seen it in the old literature, but I have not seen it before. My paper was, I think, around 2003 or so. I'd have to go back and look. But this is it's straightforward if you just write down the chiral Lagrangian for an effective field. I'm trying to think, can I find that formula somewhere? Let's go.
Well, it's also possible, if you want, you can share a screen for your paper and you can find that formula.
Yeah, that's probably the thing to do. So let me figure out how to do this. I do shift this goes over.
Actually, the comment I was trying to make next is that because the spectrum is known, if I hear more detail about the spectrum of this diagram, and if it's massive, we can ask more about the property of this massive gap phase.
Okay, so let me find.
That's the next thing. And for example, whether these are protected by a certain symmetry, is it the SPD order, or is there something else? And what are the nature of the transition? All this can be asked if we know the detail of this diagram.
All right, so I guess the first thing to do is get myself down to my, okay, so now, where am I? Because we're good on time, I'm going to shift this, put this over here. Now I've lost where I am. So what I want to do is temporarily dump this, and we'll come back to it. All right, so I think it's in the latest version of this. see. That's not it. There it is. Let's see, I can make this bigger, I think. Okay, on the bottom here. This is the chiral symmetry result for the mass of the pi naught. For the three flavor theory, with 3 arbitrary masses. And from this, you get that diagram. That's all there is to it. And there's a symmetry between the 3 masses, as there should be. And so there's another phase which I didn't draw into that picture. But is this okay? Do I still have people?
Yes, we see this.
Yeah. And so it's just, you ask, where does that the pi naught mass vanish? And it's when this is equal to these things, and it's just becomes that diagram. All right, so let's let me go back. Since I'm almost done, it doesn't really matter here. So
Sorry, but just make sure. But when the strange quark mass is 0, does that formula still apply?
well, if the strange quark mass vanishes, then this whole thing changes around, because I'm assuming here these are the 2 light ones, and I said there's another phase up in here where I guess it's the K becomes massless, because there has to be symmetry between MS and U and MD. I just wanted to keep this thing simple, so I'm assuming when you get up as far as if M up or M down is equal to MS, then there's more stuff going on up here. But it is all that one formula.
But just maybe I'm just out of the knowledge you have. So the pi 0 this Pion only have naively just contribute significantly from MU and MD, right? By new formula,
that's the dominant
yes. By new formula, it looks UDS they will contribute in a more symmetric way. In a way, you have a formula in this equation 39. So why is this? Why not maybe U and D have more dominant contribution in that formula?
Yes, they're the main part, but then eventually, I could go back to the formula. It's really the mass in that formula. It's the strange mass which is making this open up a little bit. But in reality, you should also include the eta prime. And so this will always open to some extent as this becomes non-degenerate.
It looks I'm just questioning the more like maybe there's a permutation symmetry of changing UDS in that formula, right? You can change UDS in
all three, but there's a symmetry between all 3 in that formula.
Right, but why? But this only the pi 0 mass. The pi 0 makes this Pion mass. So why the S also contribute as in the same way as U and D? Maybe I'm just not understanding this enough.
I'm not quite understanding the confusion. I mean, physics should be the same. I guess what if you make the MD might be much heavier than the. I mean, it's really a mixing between the pi and the eta, and so as if this gets very, very large, you might be calling it the eta instead of the pi. I mean, the name nomenclatures. I guess there's probably some point where I wonder if there's a point where the pi naught and the eta become degenerate with each other. Yes, probably there is.
Yeah, but I think my question should be clear: is that pi 0 is dominantly contribute from U and D quarks,
That's
but
right.
Your formula has UDS contribute in this permutation S3 symmetric way. So I was wondering why.
Well, so I mean, the Pion and the eta, which is SS bar plus UV bar minus DD bar combination, they start mixing because there's no isospin is broken. Once isospin is broken, there's nothing preventing the eta and the pi knot from mixing, and that mixing is getting bigger as these become, as isospin gets more and more broken. The isospin line is the diagonal this way, and as it's broken, there's more and more mixing, and that's what's opening this up.
Okay. Yeah, but I'm still surprised the S show up in the same way as U and D. Basically, maybe I'm just not understanding them. But thank you.
Well, it has to, because the names of the quarks are kind of arbitrary. So if all 3 quarks are equal, then you've got all 8 Goldstone bosons being degenerate. If all 3 masses were equal, you're going to have 8 particles, and the kaon and the pion and will all be degenerate. There's nothing which, well, I mean, it has to be symmetric under all 3 of those, I think.
Okay. Well, I agree they should all contribute, but I was surprised again just by the fact they all. Anyway, I don't understand, but thanks. Thank you.
Well, okay. I mean, it's just a statement that if all 3 quarks are equal, how do you tell which one is which? I mean, except for the charges, of course.
Well, they are different family, right? UD is in the first generation, S is in second.
Oh, well, that's getting into I mean, in principle, you could bring the charm in too, trying to keep it as simple as possible. Yeah, the fact that in this is just the usual SU3 limit where there's just the 3 being considered. Anyway, I've only got a couple more slides and then some possible backups. So I guess first I want to say, do we care if we can't define the quark masses precisely? See, what I'm worried about is the question, can M up equals 0 be well defined? And I'm saying, no, it can't be well defined. But it doesn't matter, because it's not what you measure in scattering. And as I said, the topology is very, very, there's a connection between the quark mass and the chiral susceptibility, the topological susceptibility, and because the gauge fields are not differentiable. So what we really should regard is only the physical particle mass and scattering as physical things. I guess they kind of come back from the days of the S matrix where if you can't measure it, it's not real. All right, so oh, I'm not on full screen, am I? How do I get the full screen? Oh, I go up to here. All right, there we go. Okay, so now what are we doing? So the basic results are that non-perturbative physics is really crucial for QCD, especially low energy QCD. And it's interesting that different theories can have identical perturbative expansions. So the perturbation expansion does not really define the theory completely. Non-degenerate quark masses do depend on the scheme you're working with. Mu equals 0 is not well defined if MD is not equal to 0, because these things get mixed together. And the gauge field topology is inherently ambiguous. The connection with topology is coming about because the Fermion determinant suppresses topology. And so the topology will vanish if the mass vanishes. So the possibility of a vanishing topological susceptibility and a vanishing single mass quark are equivalent. But topology is inherently fuzzy. Fields are non-differentiable. You can try and define topology through an index theorem with some fermion probe, but all the fermion probes we know, because of doubling problems, they depend on your lattice scheme. With Wilson fermions, you don't really have exact zero modes. They're small, and then you have to define what you mean by which modes count toward the topology. The overlap is basically derived from Wilson fermions, and it's not a unique operator. It depends on the parameter called the domain wall height. I think, yeah, this is where I stop. All right, so I think I'm done. And so now I'm ready for lots of hard questions.
Thank you, Mike, for the seminar, wonderful seminar. Question from the audience.
Mike, this is Rajamani. Can I ask you a question on the beginning part of your talk?
Of course.
How would you do a non-perturbative regularization if you don't have any masses in the spectrum, but it's strongly interacting?
You want to, well, I mean, the lattice, of course, is a non-perturbative regularization. You want something different than lattice?
No, in the lattice, let's say you don't have any masses in the spectrum. So all the baryons, they're all massless, but it's a strongly interacting theory.
Well, that's actually one.
How would you do it?
That's one of the important points. With the lattice, you do introduce a scale from the lattice spacing. And the important point is when you try and take the continuum limit of same QCD with all the quarks being massless, you will generate a scale, the lambda parameter, and the proton will not be massless.
No, but what if, let's imagine that you can put in enough flavor so the proton becomes massless. Then what do you do?
You want to make the proton massless. I don't know how to do that. If I add more and more flavors, eventually I run into the problem of losing asymptotic freedom.
Oh no, but you are not there yet. So let's imagine that there is a conformal window. And how would you, I want to see how you would do your procedure. You sort of said, keep the proton mass fixed and do the calculation. Now I don't know what to keep fixed.
If there's a conformal window, then you've got a conformal theory. At that point, I don't know, actually. If there's, in fact, a conformal window, that's a conformal theory. And of course, we know QCD is not conformal because
it
doesn't have massless particles. Yeah, so I guess you're asking if I had a conformal theory, how do I really define it non-perturbatively?
Yeah.
I guess in that case, you would have to work with this conformal theory would have some coupling constant in it, which survives. And you'd have to hold that fixed, I guess. I don't know, I haven't thought about this.
Because all propagators will go like power law. And
right.
Somehow you have to keep the propagator at some distance fixed, but I don't know how to set its scale.
I guess the only real way is some kind of, I mean, you could hold that power fixed, I suppose. This is something I haven't thought about, so
I just was curious.
Yeah, I guess I'm sort of coming from the point of view that we know QCD is not.
Yeah.
Why do we worry about it? On the other hand, no, that's a good question. I don't know the answer.
And Mike, you could have done this analysis with one flavor, right? When you were talking about.
Oh, one flavor is one of my favorite theories. One flavor QCD is fascinating because it has no chiral symmetry.
Yeah.
Therefore, all
And
particles.
what the phase diagram just has one point at negative quark mass?
I think that's the right way to say it. The theory is perfectly well behaved at 0 quark mass. It's going to generate its own masses. The masses will be the proton and the eta prime will all have masses. And then as you go down to negative enough quark mass, then that eta, calling it the eta, I don't know what you would call it, but it will get lighter and lighter. And at some specific value of negative mass, it will become massless and you'll have a second order transition. It'll get an expectation value. But it will happen at a negative mass, not at 0 mass. That's why it's such a fascinating theory. One flavor QCD is not really well understood. And to do it numerically is very difficult because of all the sign problems. Yeah. In a sense, actually, one flavor QCD, let's back up a little bit. If I let the down quark mass get very, very heavy, you leave behind the one flavor theory. So you leave behind, as you vary mu, you hit a transition, and that will occur at a negative quark mass. Yeah, so you can think of the one flavor theory as coming from the limit of a two flavor theory when you take the down quark mass really heavy. And the other interesting comment here is that formally, once one quark mass is negative, you're in the theta equals pi region. But there's a gap here where the theta equals pi region does not have any CP violation. So, you know, at theta of pi, there is a CP violation if the masses are big enough. I mean, once you reach here. But there's a gap where theta can be pi and not have CP violation when the quarks are non-degenerate. I think that's kind of an amusing fact. I probably lost everybody on that comment. But the one
No,
flavor,
I'm still here. Thank you. Thank you.
okay.
And I also didn't know this argument of Dyson about the perturbation.
Well, the argument of Dyson was just taking chiral Lagrangians and messing around. It's a totally different language. But he says,
No, I mean the E going to IE. You said that.
Oh, that one. Oh, that's a famous argument. It's
I didn't know that.
yeah, that light charges can't attract. Now you can, as long as you're speculating on such things, you can say, well, what about gravity, where they do attract? I guess that gives you the Hawking radiation where things decay. But once you got a black hole, you got lots of energy available. You can dump things into it. Anyway.
Thank you.
Maybe a naive question from maybe more quantum matter audience. A lot of people are condensed matter background. So what are the new things established in this talk, like compared to previous results? Just want to make sure what should we take from this.
Okay. I mean, that particular paper has not been published because a lot of people don't like this. It's this question of whether M up equals 0 is well defined or not. And it is in fact not, because there's no singularity here. And that's the controversial part of this thing. What else is, this is really more, it's really not, I'm really not discussing new results. I'm going back, discussing kind of the framework on which we understand these things. So I think, I'm not sure I know how to answer the question. All this stuff is actually rather old. This picture is kind of cute. But Dyson did predict such a thing. Okay, any?
Could I briefly come back to the point that Juvan raised, this symmetry in that mass formula for the Pion? You had shown that in the paper.
Oh, the formula, you want me to show that again?
Yeah, I wouldn't mind, please.
Okay, I can do that. So I have to figure out how to get out of this. I kill this. That was somewhere far down. Where was it? Yeah, this one down at the bottom here.
Yeah, 39, yeah. So again, this might be a naive question. I'm not directly in this area. How is that formula derived?
Okay, I can pull out another paper. You write sigma field, which is e to it's basically the Gell-Mann matrices times the various fields. So there'd be a pi field, e to the I pi times tau, and then e to the I eta times lambda 8. And then you ask, and then you add a mass term to that. You know, so you read, it's the old chiral Lagrange, and d mu of this sigma field, d mu is started with a Lagrange, then you add to it an m, the trace of m times this. I wonder if I can find the paper. Oh boy, I have to dig down in here.
Because I mean, in some sense, what I was wondering is, and this is basically Juvan's point, the symmetry. There's a clear permutation symmetry.
Oh yeah, no, that's required. Yeah.
And then just simply the structure of it, whether there's again another natural symmetry that allows you to see why 39 must be true.
Well, that's just SU3 symmetry. I mean, each quark is treated exactly the same. So which one you call which, it doesn't really matter. This is where something becomes massless. And
yeah, and then the second part of that question I'm asking is there something about the structure of that formula 39 which you can infer from another symmetry? Or is that is that just simply by calculation?
I think the symmetry is just required because we've written the theory symmetrically between the three quarks. I mean,
oh yeah, but yeah, I'm not asking about now the symmetry between the three, but rather the structure, the exact form of that formula, whether that is derivable by a symmetry itself, or that formula only follows from a direct calculation.
Oh, this formula certainly is going to have corrections.
So that's an asymptotic.
At higher orders than the masses, but the basic symmetry between the three things is required, because that's just, QCD has a symmetry between the various quarks. They're all treated the same.
So again, just to be clear, you're saying 39 is not an exact proportionality. There's corrections to that formula.
Oh yeah, there'll be higher order corrections, etc.
Okay, then that's fine.
So
Thank you.
This is not exact. This is exact in this chiral model where you take a unitary matrix, which is e to the I, the gamma matrix, the lambda, the Gell-Mann matrices times the fields, and then you write your masses. I could try and dig out the original paper, but that's going to take me a moment.
No, don't worry about that. Don't get distracted by that. Thank you.
Yeah, I mean, I wrote this formula back in the early 2000s, but I think this has got to be much older. Yeah.
You also make comments about Wilson fermion and the domain, maybe domain will overlap fermion in the 37th slides
Yeah.
this problem. Can you say a bit more, because you just show it but not explaining?
Well, it has to do with the doubling problem, that if you just take a naive fermion and put it on the lattice, you discover you have too many zero modes of too many states. And to get rid of it, Wilson put in a term which was not chirally symmetric, which gives a mass to the things. And the idea, well, first of all, as soon as you put that in, you're changing the, if you want to put it more condensed matter language, there's a fixed point, and you're going to not go to the fixed point where they have.
Maybe you can show that slide first, and then people may be able to follow. If you don't.
You want to go back to the. Okay, so we're talking about my comment here.
Yes.
Okay, if you look at, oh boy, let's see, what for a good, do I have a good slide for that? The eigenvalues of the Wilson fermion operator when you have, and actually it's true for the overlap fermion as well. For the overlap fermions, you do have exact zero modes, but everyone is matched by another mode at some large value, the other side of the main of the overlap fermion circle, if you want. And so there are massive particles in the theory. What do I want to do? See, there is this anomaly which is coming from these extra zero modes, and Wilson fermions do not have their modes. They're not exactly zero. Well, how do I want to say this? I mean, this is a whole topic in itself. How do you get rid of the doublers? I'm not quite sure how I want to say this. It's I guess I could dig out. What should I dig out? Well, if I wanted to dig it out, I could pull up my.
So, Mike, I guess your point is that in Wilson fermions, you will see level crossings, but level crossings won't all happen at the same Wilson fermion mass. And
Yes.
that's basically the point you want to make, that it sort of
shifted
spreads,
away
it spreads
from-
itself with different masses. And so counting topology, if you want to count it using level crossing, that statement depends upon at what Wilson mass you are counting the level crossing.
Exactly. And so it all depends. I mean, this is really more for like Rajmani. There's these circles for the Wilson operator, and eigenvalues tend to fill the middle of those circles too. And the question is, what is the density of eigenvalues there? And I think there's
at this point, I think one just has sort of empirical evidence that maybe it flattens out, but you are right. There is no proof that it flattens out.
Yeah, and I think actually a particularly interesting case is the two non-degenerate quarks, so up and down quark non-degenerate, and look at something like the overlap. You will have one circle for the up quark and another one for the down quark. And I think the question of what the eigenvalues are between those two circles is a very subtle one. I think if in the situation of Wilson fermions, where you had two different nearby masses, between those masses, I think there's going to be a lot of eigenvalues which do not go to zero. But now we're getting very technical. trying to think like it.
I think here you are trying to compare lattice schemes. I think I was just asking what are the comparison. I cannot understand the sentence, so I was just trying to ask what I mean. Maybe you can give one example. Even fix the mu and MD quark to be a fixed value. Maybe even just some constant or some zero, and then what are the implication for these two schemes? I didn't get this message. I think Rajamani comment helps, but
I think the point, well, not a completely different way of saying it is when you're working with Wilson fermions, you have a critical hopping parameter where the pion is supposed to be vanished. But that critical hopping parameter depends on the Wilson parameter. In other words, there's a shift in the physical particle masses. Oh dear. I wonder if I can, there's a question of how much time you want to take, but I can go off to the, can probably go back to the book on this. I'm getting very distracted here. I don't know how hard that would be to do. Let me kill this.
it depends whether this is one of the main point you want to convey to the audience. If you think so, then maybe you can.
Well, the reason I didn't want to get too technical, that's the problem. Let's see, what do I want to do? We're talking about the fermion thing here. Zero modes and okay, let me go to page 139. How do I do this? I pull this down with this. Let's find some good pictures. I don't have any nice pictures. Where's there? There gotta be some pictures in here. So this is what the naive Wilson spectrum looks like, eigenvalues of the Dirac operator. For the free theory, it's a bunch of circles. But as soon as you turn on the interactions, eigenvalues come out of these circles and can become zero modes. So what happens is, as you're varying the parameters of the theory, there's a certain hopping parameter which think, oh, this is getting, this is going to be really technical. That's the trouble. Oh, this. When you turn on this Wilson parameter, that diagram I had before can be opened up. This is relevant to one of the questions. Where was it? going to take me forever to figure out. Oh, this is the two flavor phase diagram as a function of all parameters. Let me back. Okay. So as you, this is the chiral condensate, psi bar psi. As you vary the up quark mass, or actually the average quark mass, it comes down, hits that Dyson boundary, and goes down to the other side. Whereas the Pion field expectation rail vanishes, goes up around the circle, and comes back on the other side. This is that one person was asking about the what's going on inside that funny face. Is this helpful for anybody? Probably not. I need to see what people are thinking.
I don't know, but I was asking the two sentences you write in the slides, and whatever you can. If this is a main point, you can say more. I didn't get this figure, but anyway.
Okay, so let's go back to where here. In this diagram, as you go down, follow some line like this. You the Pion, oops. There's a condensate, sigma. And this condensate is positive here and negative over here. And as you go down this, a line parallel to the isospin line. The condensate, there's a second order transition here. Then the condensate goes to the other side. And there's a second order transition. At these 2 points, the Pion mass vanishes. You go around the circle. This is all based on this picture of back up more. When I switch between different viewers, it's what do I want to do? Oh, I know what I'm doing here. I'm discussing the. Okay, I'm totally confused about where I'm going. Where am I going? I need a question. Is there anybody there?
Well, any more question from the audience?
Yes, which book is that?
Hello?
I didn't catch the title for the book. I'd be interested to look that up.
What should I, well, okay, so where should I be going? What do people want to know?
Maybe we can, I think the time is almost there, so we can thank Mike again for bringing the quantum math people to know a bit more about the QCD and simulations and also some non-productive aspects. Thank you, Mike, for the wonderful seminar.
Okay.
We'll ask more questions later afterwards, but thank you.